80 cents. Okay. Life is hard. Okay. Just call it $1, and then you won't feel bad. All right. Okay. So here we are, chapter 5 already. It's only the second week Wednesday, and we're in chapter 5, and this covers resampling methods. Okay, which in our textbook is basically cross-validation and bootstrap. If you took my 102B class, we've already covered cross-validation, and so today's lecture might be, I don't know, redundant. And do you guys cover cross-validation in other classes as well, other than 102B? What's that?
Somehow.
Somehow?
Yeah, we just use that in some project.
In some project? Okay. All right. Well, okay. Well, it is an important concept because pretty much at some level, at a certain point, there's less of a shift, or there's been a shift on less checking the assumptions and just checking the performance of cross-validation. Okay, so I think early on in our course we talked about, you know, there's like models that have good interpretation and are simple to understand, and we have like good inference, right? We can create models for prediction and for inference, and then we have other models that are more flexible, but maybe have less interpretability, but are, you know, better for prediction. And there seems to be a trend where almost all the machine learning efforts are going into the predictive side and less on the inference side. Okay, and so things like neural networks and, I don't know, these complicated, you know, like this gradient boosting stuff. We'll talk about boosting later, but you know, gradient boosting and all of this stuff, they get complicated, and we have a hard time understanding or interpreting or using these models like neural networks for inference. And so we can't really go back and check assumptions. You know, with like linear regression, you have like a good set of assumptions to check, right? You're supposed to have like constant variance, and you check your residual plots to check for that and stuff like that, right? And you can say, well, is my model valid? Because, and then you have all of these assumptions to check, and your whole 101A class is devoted to that. But when we say, well, we're not going to make as many assumptions and we're just trying to get predictions, how do we assess model performance? Okay, a lot of that falls on cross-validation. Okay, and so you know, in our class we're using R, but I think probably at some point in your career you should learn Python if you're planning on going into data science and stuff, right? So also plugging my own class, but I don't really need to plug it because like it's super popular as it is, right? Because but I also teach a class on Python and fitting, you know, these models in Python, and pretty much the biggest machine learning package in Python, sklearn, its model evaluation is built entirely around cross-validation. Okay, but it's not designed for you to be checking assumptions and stuff on like linear regression. You evaluate the linear regression performance by using cross-validation. Okay, and it's basically all of this stuff. And so even though you've seen it like maybe a few times before, it might be worth going over again here. You know, at least following what they talk about in this thing, and whatever. Okay, and then we'll also talk bootstrap, which I've covered in 102A. We'll cover it again here. I think it's okay. I think it's always okay to kind of see the same thing again multiple times throughout college, because it just drills it in and makes sure you get it right. That was like my entire, not my entire, But when I did grad school, I did not have a stats background. So like my first year was just like everything was brand new, and it was hard. I didn't understand half of it. And then I saw the same stuff the following year, and then the year after that. And then at some point after seeing the same thing multiple times, I was like, oh, okay, all of this makes sense. So same idea. Okay, cross-validation. Let's get into this. All right. Oh, yes, question. Did I do attendance? I think I opened this online poll. Did we respond to this? Okay, all right. Go ahead and do that. All right. Okay, so resampling, we call it such because we repeatedly draw samples from our available data, okay? And then we often refit the same model on every sample, okay? So we have our available data, and then we resample it, and we refit the same model, okay? And this process of resampling and refitting will provide information to us about the model that we're fitting, okay? And ultimately, well, I don't know ultimately, but a lot of times this allows us to compare this model that we've been refitting to a different model that we may have also been refitting, right? So when I say we refit the same model, during that process, you might actually, when you resample the data, you might fit like multiple models. You might say like, I'm considering this linear model, and I'm considering this quadratic model, and I'm considering this spline model, right? And so you resample the data, you have this new sample, and you're gonna fit all three models, and then you resample the data, and then you fit all three models again, you resample the data, and you fit all three models again. And then at the end, you refit those same three models, maybe like 1,000 different times, and then you can look at like the 1,000 different linear models that were fit, the 1,000 different quadratic models that were fit, the 1,000 different spline models that were fit, and then you can make comparisons between all the linear models, all the quadratic models, and all the spline models, okay? And so it allows us to compare, you know, our models against each other, all right? Yes, every time we refit the model to one of these new samples, we have to recompute all of the model parameters, right? Every time you fit linear regression, you got to recalculate the intercept and slope. For linear regression, that's easy. Quadratic models, you know, you've got a beta 0, a beta 1, and a beta 2, right? So maybe that's not too bad. Okay, and then a spline model, which we'll talk about later, there's a few more things we've got to find, okay? And you might be fitting these models like thousands of times, and so it can become computationally expensive, but thankfully all of our computers today are like super, like they're faster than ever, right? Every year, the fastest computer is faster than like the previous year's computer, right? And I don't know, I saw a thing on like how the animation power of Pixar has like gone crazy. And so like when they first made the first Toy Story movie like 25 years ago, it took them like, I don't know, tens of thousands of hours of computing time. And if they wanted to, they could render the entire movie today on like a single machine, like in less than the time it takes to watch the movie. Like they can render the entire movie in real time for the original Toy Story, right? But then, you know, Toy Story 4, haven't seen it yet, so don't tell me anything about it. Apparently, you know, took hundreds of thousands of hours. And every movie that they make, every year, they get more and more complicated in the animation, and it takes hundreds of thousands of hours to model and stuff. But anyway, so computing power has gotten better. And so all of these resampling methods used to take like hours or a very long time, you know, a decade ago. And now now we do them in a few minutes, okay? But even that might make you feel impatient, right? Like anytime you type something into R and you have to wait more than like 5 seconds, you're just like, But anyway, these computational methods, like they're computationally intensive, but they're useful now. Okay. So we can use to assess the performance of a model and make a selection between competing models. All right. So as far as cross-validation goes, is you know, whatever data we use to fit the model, we call that the training data. Okay. And generally, we don't want just a model that does really well on our training data, right? We want a model that will make good predictions for data it hasn't seen yet, right? So we don't want our model to overfit the training data where it's like perfectly predicting just the training data, but what will happen to new data it hasn't seen? You know, we don't want that, okay? And so to do this, we might use something called a test data set, right? And so I think pretty much on Kaggle, every single competition is done this way. They have training data available to you, and then your model performance is evaluated using the test data set, okay? So the training data has all of the answers, has all of the input variables and all of the answers, and then the test data set has all of the input variables but none of the answers. And the answers are hidden from you, and you use the test data to create your predictions, and you submit your predictions, and Kaggle will compare your predictions to the true answers, and it evaluates your score that way. Okay. And so that's how we evaluate our models. Okay, and that's how Kaggle runs all of its competitions. It evaluates, you know, your test data performance against the test data answers, which are hidden from the users. And that was that. Have you guys heard of the Netflix prize? So this is like history of data science, okay? So this is, when was the Netflix prize? It's got to be like 12 years ago now. So this was a competition. Okay, only 10 years ago. Competition back in 2009. So Netflix, you used to rent actual DVDs, and they would send DVDs to you in the mail. And then their CEO was like, you know what, the future is streaming. And this was at a time when nobody streamed anything. And then they were like, we're gonna make a service, and we're gonna make streaming and things. And then, anyway. And then so they wanted this prize for like, they got rid of the star rating, right? Now it's like 97% match or something, right? You guys have Netflix or you don't? Okay, like only 2 of you have Netflix? You guys have to get Netflix. It's excellent, okay? It's like the best $10 a month you can spend, or whatever it is now, all right? It's, okay, maybe not. Maybe you should study. But anyway, they had this prize, and they said $1 million if you can make predictions on like how users will star a movie, okay? And so, and they had like this huge catalog of movies, and they wanted to know, like, you know, are the users going to give it like this many stars or this many stars or whatever? And so they had a big competition, and I would say this is one of the big things, because like it was like $1 million to analyze data. Like no one had ever heard of such a thing, and this, along with a few other things, I would say were really instrumental in getting the concept of data science really popular, okay? And so now statistics and data science as a thing is like super popular, and everybody wants to do it, and there's a ton of money and a ton of jobs available. And it's quite competitive to get into grad programs for statistics and data science. And I always tell everybody that I'm only here because I said I wanted to study statistics when nobody else wanted to, and they allowed me in because I was not a competitive candidate. But I liked it, and here I am. So, okay, but anyway, they basically had training data, and then and test data, and you would make your predictions on the test data, and your model was evaluated against everybody else's, and whoever had the best predictions did that. Okay, so but a lot of times we don't have this test data available, and we only have one set of training data, right? We only have one set of data available. So what should we do? Okay, and so there's a few different strategies, and one is to take the available data and then split that into training and validation sets. Okay. And actually, further today, I think your best practice is if you have a certain amount of available data, you're going to split that into the true test data, okay? And you split this, you take off a chunk, and this is not going to be touched ever until the very, very, very end. And then you have your available data, your non-test data, and you split that into training and validation. So you might be making three sets. You got training, validation, and then kind of your true test data. And your true test data you never get to touch until the very, very end of your project. But here we're just kind of talking about this idea of taking the available data that you have for training, and you further split that into training and validation sets, okay? Or some might call it a holdout set. And so the simplest idea is, here's your available data. You kind of mix it up, okay? Instead of going 1, 2, 3 all the way up to n, you're going to just mix them up, and so you shuffle them, and you put some of them into the blue, which is going to be the training, and you put the other into this orange or beige, and that's going to be your your validation set, okay? And so by random chance we get observation 7, 22, 13, and a bunch of others in the training set. By random chance, observation 91 ends up in the validation set, but there's also a bunch of others. We use this to estimate our model parameters, like your slope and intercept, or whatever spline you're fitting, whatever model you use, you fit it to here, and then you have it predict all of the points over here, okay? And all of these actually have the answers, so you can make your predictions, and you can compare your predictions to the actual values in your validation set, and you get an idea of how good or bad your predictions are. Okay, and so so the example that we have in our textbook is they use the auto data set, and in the auto data set we want to predict miles per gallon versus horsepower, okay? And so fuel economy versus horsepower. In general, if the car has more horsepower, like it's a big truck or it's a sports car or something like that, it's not going to be very fuel efficient, right? It's going to use more gas. And if you have less horsepower, you've got like a little car, it's going to be more fuel efficient, right? Like the little smart car or something. Not a lot of horsepower, more fuel efficient, okay? And then and so if we look at this, fitting a straight line model might miss important aspects. Fitting a quadratic model will do better, and fitting higher degree polynomials will also reduce the training error, right? So as we increase the number of terms, our training error goes down. So this is the data that we're using. And we can ask, well, what's the best model to use? Well, the goal shouldn't just be to reduce the training error only, right? We want to have the minimum test error, okay? But again, the test data is not available to us, so we're going to use the validation set to kind of give us an estimate of the test error, all right? And so here, this is a plot of, let me actually pull up what the here's chapter 3. All right, so this is the real plot between horsepower and miles per gallon. Okay, and so the linear model doesn't do good, and this is using all of the available data. Okay, and here's a degree 2 polynomial, and it does a better job. In degree 5, actually this extra curvature and stuff reduces the training error even more. Okay. But we saw, I think, you know, back in one of these things, that reducing just the training error, it shouldn't be our goal, but we want to reduce the test error. Okay? And so this is what we have, is that, you know, here we've got our training set and our validation set. And on the left, if we look at how increasing the degree of our polynomial, fitting a straight line to a quadratic, cubic, 4th degree, what is that, tetra polynomial or something, okay? And then 5th degree, order 6, and stuff like that, you know, there's a drop to go from a straight line to a quadratic fit, but we don't get a whole lot of improvement after that on our validation set, okay? On the training set, the error is going to keep going down because more flexibility, you can fit your training data better. But that's not our goal. We're trying to fit the test, or our validation data, right? And so on the validation set, you know, we probably will say, okay, let's just go with the degree 2, okay? So what is this graph over here? Well, if we think about it, this is just one possible validation set, right? And if somebody else says, well, what if I scrambled up my observations in a different way and I put different values in my training set and different values in my validation set, okay? That's still the same approach, but we're just getting different observations. So maybe we don't get observations 7, 22, and 13, but maybe we get observations 5, 53, and 18, and whatever in our training set, okay? Well, if we do that, we get very different mean squared error things, okay? We all see the same drop going, so here if I trace whatever color this is, this brown line, we see a drop going from a straight line to a quadratic, and then going up to changing the order of the polynomial, you know, it goes up and down and fluctuates a little bit, right? This yellow line down here, it starts off high, going to a quadratic, drops it down quite a bit, and then it fluctuates. So we see the same general trend of going from straight line to a quadratic, drops it, and then going after that, it kind of fluctuates, goes up or down or stays flat. But the values themselves vary quite a bit, okay? And that's the problem with just using one validation set, okay? You got one training set and one validation set. You don't know if this line is, you know, one of the low sides or on the high side or whatever. We're not quite sure, okay? And so using just a single validation set may not be the best approach, okay? So drawbacks of using only one validation set is that, you know, the estimate of the test error can be highly variable depending on the data points that were selected to be in the validation set, right? So we see all of this variation between different possible validation sets. And then, again, only the values that were selected in the training set are used to fit the model. And thus, if we did a 50-50 split, only half of the values are used for training the model. And having fewer observations to train the model is going to result in poorer model performance, right? The less data you have available to train your model is going to result in models that don't perform as well, okay? And so this often leads to overestimating the test error, okay? Because the model you're fitting isn't going to be very good, and so you're going to get more error when you do the validation set, and you end up actually overestimating the test error. I mean, maybe that's okay. It's kind of a cautious, conservative approach, but generally, you don't want to overestimate or underestimate in general, right? You want to get as close to the real thing as possible. Okay, so that's one drawback. And so kind of to combat that, another idea is leave one out cross-validation, okay? And so leave one out cross-validation will take the entire data set and use everything as the training set except for one observation. One observation is the validation set. So one observation is used in the validation set. Everything else goes in the training set, okay? The models fit on everything else, the n-1 observations, and then the error is calculated for the one observation in the validation set. So you've got one observation here, and you know its real value, and so you can calculate the error there. And then you do this for every single data point. So you're going to do this n times. You're going to fit the model n times. So if you got a big data set, you're going to fit this a lot of times, right? And then, so every available observation gets a turn at being the validation observation. Okay. And then the leave one out cross-validation estimate of MSC of the mean squared error is the average of all of these mean squared error values that are calculated. Okay, so we do this for all of them, and then we divide by n. Okay, so schematically our diagram looks like this. Okay, so you've got n observations, and in the first run, observation 1 is your validation set. Observations 2 through n are in your training set. Okay, and in the second run, observation 2 is your validation set, okay? And then the training set is going to be observation 1 and observations 3 through n. And in the third one, observation 3 is your validation set, and then everything else, observations 1, 2, and then 4 through n are your training data. And you do this all the way until the very last one where n is your validation set. So you got to fit the model n different times. Okay, is that okay? So that's leave one out cross-validation. And so you fit the model on everything but one observation. And then you just see, well, how well did it predict that one observation that wasn't used? Okay, so the advantage is that the fitted model uses almost the entire data set, okay? So we're only missing one point when we fit a model, okay? And thus, leave one out cross-validation generally does not overestimate the test error. Usually it gets a pretty good estimate of whatever the test error is in the long run, okay? There's also no randomness to leave one out cross-validation, okay? So if I did leave one out cross-validation on my data set and you did leave one out cross-validation on your data set, we're going to get the exact same answer, okay? Whereas if I did a random set for validation and you did a random set for validation, our validation sets will be different, and so our error estimates are going to be different as well, okay? Leave one out cross-validation, there's no randomness. So you and I are going to get the same answers, okay? Disadvantage can be computationally expensive, right? If you've got like 10,000 data points, you've got to fit your model 10,000 times. And maybe we don't want to do that, okay? You know, shortcuts exist for getting like the leave one out cross-validation value for simple models like least squares regression and stuff like that. There's a shortcut to evaluate this. But in general, the idea of leave one out cross-validation is computationally expensive because you've got to fit the model n different times, okay? However big your data set is, you've got to fit the model n times, and if your model's complicated, like a neural network or something, you know, this is not the way to go. okay, where it takes a long time to train your model. Okay, and so kind of another approach is k-fold cross-validation, okay? And so in k-fold cross-validation, rather than using each observation as the validation set, you're going to take your entire data and you're going to split it into k pieces, okay? Or you call them folds. And so usually there's a random element here. You usually shuffle up some of your observations. You break it up into k different chunks. We often, for no good reason, well, I don't know, probably because of how many fingers we have, we'll often use k as 5 or k as 10, okay? But there's no rule about how big k should be. You can use k as 6, k is 14. There's no rule, okay? But you often see 5-fold and 10-fold cross-validation, and I don't know why. I think it's just because we've got 5 fingers on our hand. That's like the basis of like our entire number system, right? So that's like a topic of sci-fi movies, right? When you encounter an alien race and they have 3 fingers on their hand, you know, their counting system is base 3. I don't, okay, anyway. So anyway, you do this, you fit your MSE, you calculate the mean squared error on the validation set, and you do this for every single fold, okay? And then you take the average of the mean squared error values, right? All right, so is that okay? Okay, and so the diagram looks like this. So again, so we've shuffled up the data, okay? And so here's random 11, 76, 5 ends up in the validation set for the first run. Everything else goes into the training set, okay? And then here's a different chunk of 5, different chunk of 5, different chunk. I mean, so we split this into 5 things. They're supposed to be about the same size, but you know, if you're doing 5-fold cross-validation and you have 103 observations, you know, one of your sets is going to, you know, a few of your sets won't be exactly the same size, right? So maybe you'll have 3 that are 21 and 2 that are 20. I don't know, something like that. Okay, so we do this, and that's k-fold cross-validation. Okay, any questions on this? All right, and so yes.
For each chunk, so they have the set observations.
What do you mean each chunk? So each fold. Yeah, so each fold should be about the same size. Okay. Now sometimes it's not possible because it doesn't divide evenly, but they should be approximately the same size. And most computer implementations of k-fold cross-validation tries to respect that, okay? And so, but depending on, you know, which package you use, it might be slightly different, okay? And there is still a random element to it, okay? Because you don't just do observations 1 through 20 goes in the first fold, observations 21 through 40 go in the second fold, and 41 through 60 go in the third fold. Usually you scramble them, you shuffle, you know, your first observations, and then you take the first 20, which could be observations 11, 76, 5, and something like that. So you shuffle them up. So if I do 5-fold cross-validation and you do 5-fold cross-validation, our answers will probably be similar, but will also be different because how you scrambled yours in the beginning will be different from how I scrambled mine, okay? But again, leave one out, cross-validation, you and I will get the exact same answer because we're going to do each observation is the validation set once, okay? And so that's what these graphs show, okay? So so here with leave one out cross-validation, we go from, this is still using this, I don't know what I did with it. The horsepower versus miles per gallon. And what degree polynomial should we fit? We see going from straight line to a quadratic drops it, and then it kind of levels out. Okay, and so this is leave one out cross validation, and again, everyone would get the same if we all did this. Okay, and here this is tenfold cross validation. Okay, but it was run 9 different times. Okay, and so each time it runs, the only difference really is just this initial step when it scrambles, when it shuffles the observations to decide which ones go into this fold and this fold and stuff. So we get slight variation, but we see they end up very, very, very similar to each other. Okay? Yes, variation, but similarities, right? If we compare that to this, where we just had one validation set, okay, we see there's lots of variation here. Okay, over here, these values end up a lot similar. Okay, it's the average of the kind of the tenfold cross validation there. Okay, is that all right? Okay. So leave one out cross validation is just a special case of k-fold cross validation where k is equal to n. And then k-fold cross validation reduces the computation expense by fitting the model only k times. So rather than having to do one for every single observation, we only have to do it k times, one for each fold. So usually a lot less computationally expensive. So that's nice. Okay. If we talk about, how good is cross-validation, right? So earlier we said the reason why we want to do cross-validation is because we want to get an idea of the kind of the error performance on the test data, okay? And so cross-validation is good for that, okay? And it can also be used to figure out, another reason is to figure out the location of the minimum error of the test data, okay? So back here, we want to know what degree polynomial we should fit on our model. Should we fit a linear model? Should we fit a quadratic model, a cubic model? What degree polynomial should we fit? And the cross-validation helps us pick that answer. It says, okay, probably just fit the quadratic, the degree 2 polynomial. So cross-validation is useful for that. And then it will also give us an idea of, the performance of our model on test data, okay? And so the question is this actually a good strategy? Does cross-validation work the way we want it to work? Okay, and so to kind of figure out if cross-validation actually does work the way we want it to work, we have to rely on some simulation, because in reality we don't know the test data that's unknown to us, right? So using cross-validation to estimate the test error, it's a tricky thing, because we don't know exactly how much MSE there is in the test data, because we don't know the exact model that exists in the population, okay? But if we use a simulation, we can know the answer, right? We can know what the true test MSE is, and then we could compare our cross-validation's estimate of that, and we could say, okay, well, how well does our cross-validation perform versus the true answer that's available in the test MSE. Does that kind of make sense? So, because the idea is, I want to know, is this cross-validation approach, is this a good strategy in general, right? And to know this, I'm going to have to rely on a simulation. So to do this, we're going to revisit some models that were created back in Chapter 2 when we were talking about kind of the trade-off between flexibility and test MSE, right? And back in chapter 2, we were fitting like smoothing splines with different levels of flexibility, and the least flexible would be basically a straight line, and that would and then the most flexible ones would be able to fit the training data almost perfectly. Okay, but back in chapter 2, again, those were simulated data sets, and so we were able to see, okay, the training data goes down when I use a very flexible model, but if I generate a new data set because it's simulated and I want to know the test MSE, we see that on the very flexible models, the MSE on the test set goes up. Okay, and so so with cross-validation, we're going to divide the available data into a training set and validation set, and then we're going to estimate the test MSE using the validation set. Okay, so here we're just revisiting chapter 2. So this is not using cross-validation. Okay, this is just talking, here is our training data, and we fit a straight line, and we fit a flexible model, okay? And then the black line's the true curve here, okay? And there's actually three lines. I don't know if you guys can see them. There's an orange, blue line that's pretty smooth, and then this curvy green line, okay, which is very flexible. And so, when we use the very flexible model, the training error goes down. That's the gray line. The training error keeps going down. More and more flexible models will reduce the training error until it actually fits every single data point perfectly, okay? But when we look at the error in the test data, which is possible because it's a simulated data set, we see that the blue line is best, and these very flexible models don't do a good job, okay? So I don't know if you remember this from last week. It feels like it was so long ago, but this is what we did back when we were talking about chapter 2, okay? And then and we did this 3 times. We had different things, and so this was another one where we had kind of straight lines, and basically the straight line and the slightly curved line do pretty good, but the very flexible models, while it reduces the training error, the test error actually goes up, okay? And then here's another one, and we can see that the straight line model is very bad. As we make the model more and more flexible, the training error keeps going down, but the test error actually goes up a little bit, okay? And so these red lines are the true test MSE curves. Yes, question?
How is the flexibility measured?
How is the flexibility measured? Okay, so this is a spline fit, and we haven't talked splines yet. Okay, so splines are non-parametric, and they're basically based on like how many quote knots you put in the spline. And I don't know, have you ever used this thing on PowerPoint? Like oh wait, where's my thing? So if I want to draw something like this in okay, so okay, so this is technically what we call a spline, and in format shape. Oh, no. So if I want to change this is called edit points. And so these are like the quote knots that appear in a spline, and you can form how these things go. Okay, so this is technically the curve that this thing makes is modeled via some mathematical thing. Huh? I think on this thing they are inflection points, but basically we'll look at this in chapter 7. You can fit splines, and they're cubic splines, and basically we try to make the second derivative continuous, okay? And that's how we make our things smooth, okay? But everything else can be discontinuous. So anyway, basically, if you add more of these points, okay, if you add more of these kind of locations, you can get a very wiggly thing, and I'm not 100% sure, but this flexibility measure is kind of a reflection of how wiggly we can make our spline, okay? So this is, you can kind of think of this as like having 20 of those inflection points to put on this very curvy spline, okay? And again, I'll talk about the math very briefly, but effectively on R, you can just say fit a spline and I want this much flexibility, and it will do it, okay? And it will do a good job because the math has been solved for us, okay? But yeah, so what did I say? Okay, so this is what we've got. Okay, so pay attention to these red curves, okay? So this is the red curve that we see here, and then here's the red curve on the second graph, and the red curve here, okay? Because these red curves, this U and this, I don't know, whatever, looks like an exponential curve almost, and then this like ski slope, they form the blue lines, okay? They change the color on us. They are the blue lines in these three graphs, okay? And so these blue lines are the MSE curves that we know because we've simulated the data, so we know the true test MSE curve, okay? So we know those things. All right, what are these orange lines and dotted lines that look almost the same? These are the estimates of this curve based on cross-validation, okay? So again, when we do cross-validation, we don't have access to the test data set because we don't really know what the true model is, but again, when we're simulating it, we can do it, okay? So if we only have one set of data available to us, and then we split it into kind of training and validation sets using either leave one out cross-validation or k-fold cross-validation, we can get an estimate of the relationship between model flexibility and mean squared error, okay? And so what, you know, just like back here where we saw increasing the degree of the polynomial changes the mean squared error, it goes down and stuff like that. We see the same kind of thing here, whoops, where increasing the model flexibility brings down our mean squared error, and then it starts to go back up, okay? For a different model, you know, it goes down a little bit and then it shoots up, and then for this one it goes down and it shoots up, okay? And so what we see is that as the dotted line is the leave one out cross-validation error estimates, and then the orange line is the one for tenfold cross-validation. And so we see the leave one out and the tenfold cross-validation, they end up quite similar to each other for this one training set of data, a set of available data for us, and depending on how we split it, leave one out versus k-fold cross-validation gives us pretty similar estimates, okay? And what we see, though, is that, you know, this curve, this U, kind of the shape matches, but there's quite a bit of difference, right? This blue line is actually like way higher than what this orange and dotted line is, okay? And these two things, they're pretty similar over here. The true values and the estimated values are very close, but then they diverge here. Over here, the estimated and the true values are almost identical, so that's a good sign, okay? Okay, so what this tells us is that, you know, if we wanted to know what this true MSE is going to be, like the actual value, cross-validation may not give us the best estimate for what that quantity is, okay? Like if we want to know that the true test error when the model flexibility is 5 is going to be around 1.0, you know, we're going to give it the wrong answer. We're going to guess it's like 0.6 or 0.7, okay? You know, depending on the circumstance, okay? Over here, we'd probably get a answer that's close to the real thing, and over here we get an answer that's close to the real thing. But, you know, in some of the cases, we're going to be off, okay? However, these little x's represent the lowest point, the location of the minimum test error, okay? So when we simulate the data, we can say, oh, we should use model flexibility 5. That's going to give us the best performing model, okay? If we did cross-validation, okay, it would tell us, yeah, we should use model flexibility something around 7, but actually probably anything between, and according to this picture, anything between 5 and 10 probably good enough, okay? Which, according to the real picture, is pretty close to the real answer, right? And if we use cross-validation, so if we know the true answer, we know the true answer says model flexibility on this thing should be around 3 or something like that. If we use cross-validation, it's going to say probably anything between 2 and 5 is good, okay? Where the absolute minimum is at 5, but really it's not much of a difference between here and here, right? And then if we look at over this one, it's going to say, you know, what model flexibility should we use? It's going to be right around 10, okay? And so, so cross-validation does a good job of telling us basically which model we should use. How flexible should I make my model? Should I use the rigid model, or should I use the very flexible model? Cross-validation gives us a pretty good idea of how much model flexibility we should have, or, you know, which of these models we should use. So cross-validation is good for that. However, if you wanted to know the exact amount of test error you're going to have, it might not do the best, right? It might be off depending on the model. Right? Maybe you're lucky and it gets it right on the nose, but you can't expect that all the time. Okay, does that kind of make sense? So how we can use cross-validation for all of this? Okay. There is something to talk about regarding the bias-variance trade-off for cross-validation, right? And so, so based on what I've told you, you might feel like, well, let's just leave one out cross-validation all the time, okay? And especially if I've got a really powerful computer and fitting n models will take like 1 minute, and fitting only 10 models for k-fold cross-validation takes, you know, 2 seconds, you know, I can wait 1 minute if it's going to give me better results or something, right? So the question is, should I just always use leave one out cross-validation, okay? And the answer is no, okay? And this might be surprising. It is true, this is true. Leave one out cross-validation leads to low bias in the estimate of the test MSE, okay? So if I run leave one out cross-validation to estimate what the test MSE is, it's going to have low bias, okay? So what that means is that, you know, in this picture, it sure seems like my leave one out cross-validation is quite a bit different from this one, okay? But depending on my training data, the data I was using, I might get a different curve, okay? And in the long run, the leave one out cross-validation is going to give us kind of your least amount of bias, okay? But here's the issue, okay? In leave one out cross-validation, you're using pretty much n-1 data points for your training data, right? So if I look at this training data set and this training data set, pretty much n-2 observations are going to be exactly the same between this data set and this data set, right? And there's only really just one observation that's over here and one observation that's over here that's uncommon. So pretty much all the training sets look almost exactly the same. And so the estimates of the mean squared error that you get for leave one out cross-validation, they're all going to be very, very, very highly correlated, okay? And so this sounds like it should be a good thing, right? And the answer is yes and no. The problem is that when you use leave one out cross-validation, you are still depending on the data that's available to you. And so your estimate of the test MSE is very, very, very dependent on the data set that's available to you. And if someone else gathered a new data set, and their data set is a little different from yours, they will get a very different, I don't know about very, but their leave one out cross-validation estimate will be different, okay? And so, so in the long run, if you do leave one out cross-validation, all of those estimates of the test MSE will have very little bias. It will get very close to the true test MSE in the long run. If this guy does leave one out cross-validation on one data set and someone else gets a different data set and does leave one out cross-validation, and someone else gets a different data set and does leave one out cross-validation, and you do this a bunch of different times, all of those different estimates of test MSE in the long run will average out to be very close to the true test MSE value. There's very little bias. However, this person's leave one out cross-validation number and this person's leave one out cross-validation number and this person's leave one out cross-validation number will have more variance because it's very dependent on the data set that was available to them, okay? So k-fold cross-validation, on the other hand, because you're only using, like if you have 5-fold cross-validation, your folds, your training sets end up looking quite a bit different from each other. And by kind of introducing the variance within your cross-validation run, you're making it a little bit more robust in terms of the variation you'll see overall. So you're going to get, if you're doing 5-fold cross-validation, this fold might produce a different number and this fold might produce a different number. Your 5 different numbers will be quite a bit different from each other, but when you average them out, you're going to get a number, okay? And then someone else takes an entirely different set of data and they do 5-fold cross-validation. Their 5 numbers will be quite a bit different from each other, but when they average those 5 numbers, they get another number, and that person's number and this person's number will end up showing less variation, okay? So because you're basically inducing a little bit of bias by kind of handicapping or giving some kind of, making it a little bit more difficult for yourself by using less of the data available, like 80% of the data for 5-fold cross-validation, and introducing some limitations there, you end up making it a little bit more robust in terms of how dependent it is on the actual data set that you are using. I don't know if that makes sense, so the answer isn't always leave one out cross-validation, okay? So leave one out cross-validation will give you the less bias, but it just makes it very dependent on the data that you are using, okay? The available data to you will have a strong determination on your leave one out cross-validation numbers. Okay, whereas k-fold cross-validation introduces a little bit of bias, but it does reduce the variance, and that if somebody else uses a different data set, available data set, the variance between numbers will not be as great. Okay. Why don't we take a 5-minute break here? I guess we'll come back at 1:15, and then we'll finish up. Okay, so the last thing to talk about is cross-validation for classification. And I didn't bother really with any graphs and stuff for this thing, but I guess we can look at the graphs that show up in the textbook. Basically, exact same idea. You split the data, available data, into training and validation sets, and then you evaluate your model performance on the training and validation sets, right? And so probably the most common way to measure model performance for classification data is using the error rate, which just says how many times did I misclassify something, okay? And cross-validation will give us an idea of how that does. So if here, we'll just take a look. So this is kind of the average, the error rates, okay? And so for leave one out cross-validation, you know, you're gonna just kind of, you know, count how many times an observation is misclassified. And as far as for leave one out, there really doesn't even need to be a sum here because it's just one observation point, right? It's just, did you classify the test case correctly or incorrectly, okay? And you do it for, I mean, I'm sorry, yeah, I guess you add this up across all n fits, okay? But the error here is just whether it was correct or not on the test case, okay? And you do this, and you just kind of get the average error, right? And then same thing for k-fold, and it's just you do it across the k different sets, okay? And so here's an example where we are fitting, you know, we're using some kind of boundary, okay, some kind of basically a logistic regression boundary to draw where this should go, okay? And you know, we can fit different degree fits and just measure the error rates here, okay? And so here is, you know, if we use different polynomials, okay, we can see that the training error in blue generally keeps going down as we increase the flexibility by increasing the polynomial boundary that gets drawn. And then the tenfold cross-validation and the test error, again, in this case, this is all simulated because we have access to the true test error, and we can see, you know, these things as far as using the test data and the cross-validation, we're getting something close. It says degree 3 versus degree 4 in terms of which kind of polynomial we should use, okay? Over here, there's no graphs of this, but this is using k nearest neighbors, okay, to classify. And for whatever reason, they've done 1 over k. So this is basically using 0.1 is using 10 nearest neighbors, 1.0 is using 1 nearest neighbors, right? 0.5 is 2 nearest neighbors and things like that. And then 0.01 would be 100 nearest neighbors. Okay, and so with k nearest neighbors, basically the fewer neighbors you're using is more flexible, and too many neighbors makes it inflexible. And so anyway, using this and this, we see that for the test error, we're getting something, again, similar using cross-validation versus knowing the actual test error cases. And so here, the test error says something around probably like 11 nearest neighbors, and k-fold cross-validation. Tenfold cross-validation says maybe we should use like 8 or something nearest neighbors. So something in the similar ballpark, okay? Again, a lot of times we use cross-validation to try to figure out the parameters, the kind of the hyperparameters of the model, right? Like how many nearest neighbors we should use or what degree polynomial we should use. And cross-validation generally does a good job, okay? And again, you know, with the KNN classifier, using only one nearest neighbor will get the training data perfect, but won't get the test error, test data case as well. Okay, but I don't think a whole lot needs to be said for cross-validation and classification. Okay. All right, and then the other bit of our chapter, and I only wrote a little bit here, is on Bootstrap. Okay, and we cover Bootstrap in 102A, or at least my class for 102A covers Bootstrap. But you know, it's worth seeing again because these are kind of concepts that we use frequently, and this is truly a resampling method. And the idea with Bootstrap is that it can be used to estimate the uncertainty associated with some estimator, right? So, so a simple example is, based on your data, you are estimating a regression coefficient, right? So you might be doing simple linear regression and you're getting the estimate of the slope, okay? And we always recognize, right? Because we're statisticians, we always know in the back of our mind that the data we have is just a sample. And somebody else could go to the population, get another set of data, and get a slightly different sample, right? And so we know there's variance in the estimate we have. We only have one estimate because we only have one set of data, but we always know that in the back of our mind that if somebody else got another sample of data, they could end up getting a different estimate, and their estimate could be different, right? And I think this is something that, you know, as statistics majors, this is something that's very intrinsic to our thinking, that my experience is not necessarily the same as your experience or someone else's experience, right? And I think this is something that maybe the greater world is not fully aware of, and they see one set of data and they think this represents the population. But we are always aware that the result of one survey is not necessarily going to be representative of the population, and that if somebody else did the same survey on a different day, they could get different results, right? So anyway, we can use Bootstrap to estimate kind of the standard error of this regression coefficient estimate, right? This example is not super compelling because we can estimate the standard error, or we can get it using math, right? Using the central limit theorem, and like we know what the standard error should be based on mathematical theory, okay? But again, if you don't want to deal with that, you can use Bootstrap, okay? Here's maybe a slightly more complicated example. I don't know if it's a great example, but it's the one that the textbook uses. Don't even bother with this math, but it's just to give it something a little bit more complicated, where we can't just say, well, why don't I just use the central limit theorem to get my answer, okay? So here, let's say there's two investments, okay? Like like if you're gonna invest retirement money, you can invest it in like risky things like the stock market, or things that are a little bit more stable like bonds, right? And or maybe it's like or maybe you're talking about like your retirement thing, and should you invest in something that's pretty I don't know, like the S&P 500, which is like the entire stock market, versus the I don't know, they have like different indices, like the emerging market fund, which invests in like these nations where you might experience huge economic growth, also maybe politically unstable, and could go through an economic collapse, right? So, you know, there's a thing, right? And so anyway, we're going to invest a proportion alpha in X and 1 minus alpha in Y, right? So we can split it 50-50, or should we do mostly X, mostly Y? Okay. And basically what we want to do is we want to minimize the risk of our investment. And so we want to minimize the variance of alpha X plus 1 minus alpha Y. And if we do some math, so this is not necessarily the strategy that everybody wants to use. Not everybody wants to minimize the risk. Some people will say, let's maximize the expected value, right? That's like another strategy, right? And so that's going to be something entirely different. But here we might say, let's minimize the risk, okay? And so, you know, if we do some solving here and we skipped all the math, we're going to say this is how we're going to minimize the risk, right? And we're going to say alpha should be this, and we look at how much variation is there in y, how much variation is there in x, and how much covariance is there between x and y. Because a lot of times, if the market's doing good, then everybody's doing good, right? So there's going to be covariance in these different estimates, right? And so the problem is we don't know the exact values of the variance of y or the variance of x or the covariance of x and y. Those are unknown to us, okay? All we can do is we can look at like the market and say, well, how did x perform? And how has y performed? And should I, like, does it go up or down or things like that, right? And so we can use a sample to get an estimate of the variance, right? So we can use our sample variance and our sample covariance to estimate what these things should be, okay? But because we're using our samples variance and our sample covariance estimates, that introduces additional uncertainty because our sample values are not necessarily the same as the population values, right? Okay, I didn't put this plot in, but this is again, this is all simulated examples, right? Our book uses a lot of simulated examples because we're often talking about the relationship between what happens in the population and what happens in our data. And the only way we can talk about what happens in the population is by basically simulating the population. Okay, so here we're basically saying, okay, how much did X change that day, right? So you're looking at the market, right? And you look at the, you know, it started off at 100 and it ended at 102. So that's good, it went up, okay? Or on another day, it started at 102 and then it went down to 101. So it goes down -1, right? And how much did Y change, right? And so this is just, we simulated some values of what happens to X and what happens to Y, okay? And then we ran another simulation and with what happens to X and Y. And we're getting similar but slightly different things, right? And so each of these things will have different estimates of the variance of X and the variance of Y and the covariance of X and Y. So we're all going to get slightly different values of these things. And so when we plug them in to here, right, if we use our samples variance and our sample covariance, we're going to, based on our sample, we'll have kind of the estimated investment strategy, right? So our investment strategy will say, okay, well, let's use our sample variance and our sample covariance, and we're going to get some estimated proportion that we should use, right? And so depending on the random sample of data we have, right? So maybe in our random sample of data, like there's a huge outlier where X goes -3 or something, right? So maybe this was like, for whatever day, reason, there was a really bad day in X. And so this is suddenly going to make X look like a much more riskier investment. And so if this happens to be your sample of data, you might say, well, let's not invest in X that much, right? And on the other hand, you might get like another thing where, Y happens to have a thing. And so if this is your sample of data, you might say, okay, well, maybe we shouldn't invest in Y as much, right? So depending on the sample of data, right, like whether you were looking at Apple stock in the 90s or Apple stock in the 2010s, you're going to have different opinions about what kind of company Apple is, right? So in the 90s, Apple was doing terrible and nobody wanted to buy Apple stock. And now Apple's like super profitable and everybody says, let's buy Apple stock. So depending on the sample of data you have, your investment strategy will differ. And the question is, how good is my estimate that's based on a sample compared to the true value in the population, right? And so because it's simulated, we know that the true value that we should be using for alpha is 0.6, okay? And what we've done is we've simulated 1,000 different values. We ran the simulation. So this is not Bootstrap. This is running a simulation, okay? This is running a simulation, and we did this 1,000 times, and we got 1,000 different estimates of alpha hat, and we got 0.5996, okay, which is very close to the true value that should be happening, okay? Okay, so we can do this with simulation. We can also get the standard error of our estimate and something like that, okay? Simulation only works in a simulation, okay, where you know what the population looks like, where we know what the values of x and the values of y should be like in the population. The problem is that we don't have access to the population, right? So I called this cheating with simulation. It's not cheating, it's just getting the numbers via simulation, okay? But with Bootstrap, you know, generally we don't know what the population looks like. And so what we do is we run Bootstrap instead, okay? And I think this is the last slide I actually created. But the idea here is in Bootstrap, we have our data, the available data to us. This is our sample of data. And what we're going to do is we resample our data with replacement. We resample our data with replacement, okay? And effectively, the idea behind that is that we are assuming that my sample is representative of the population, okay? And so what I can, if I assume my sample is representative of the population, I can just take my sample and make a bunch of clones of it, okay? I can just take my sample and clone it and basically make copies and make like 1 million of these copies. And now I've got a big thing of observations that I can treat like the population. Does that kind of make sense? So I'm just taking my sample and I'm just duplicating it, and I'm going to say, well, this is what the population looks like, okay? Now, obviously, if my sample is not representative of the population, this is a problem, okay? This is going to be a problem if my sample is not representative of the population. But we're hoping that it is, okay? And so I duplicate my sample a bunch of times, and then I say, this is my population, and let's draw a sample from this fake population that I've created. That's Bootstrap, okay? And so it's the idea of, I wish I could do simulation. I wish I could go to the population and draw new samples and see how much my estimates vary. That's what I wish I could do, okay? But I don't have access to the real population. So I want to do the same idea of simulation where I'm redrawing from the population, but I don't have access to the population. So what do? I'm going to just get my fake version of the population by taking my sample and effectively duplicating it a bunch of times. Basically, I just sample with replacement, which is conceptually the same. And we're going to say this is going to be my population, okay? And then we basically run what we did in the simulation, all right? So I do this and I resample my data a whole bunch of times, and I sample with replacement, and and it turns out that most of the time Bootstrap does a good job, okay? If your sample looks like the population, Bootstrap is going to do a good job, okay? Now, if your sample does not look like the population, Bootstrap will do a bad job, okay? And that's the catch. We don't know if our sample is good or bad until somebody else tells me otherwise, right? We're always just kind of assume, that's all we can do. Like, you go out and you collect data, you try to do your best, right? You follow all the procedures to get a random sample, which is actually really hard to do, right? There's no class where you have to do sampling, is there? 101B, you do experimental design with the island. And why are you guys laughing? You guys do that, right? And then, and I think the island makes it like impossible to do a random sample, right? Like you have to like go to each city and then go to like their history records and you find out like who married who and stuff, and you try to, like, they purposely make it hard because in real life it's really hard. Like if I told you get a random sample of people who live in Westwood, it's like not possible to do it, right? Like even if I just say like, oh, let's do it in our neighborhood, like you'd have to go to the city center and get the history records of the city or something. So the idea of getting a random sample is really hard, but let's say you've gone through the trouble. All you can do is you can hope that the sample you have is representative of the population, right? And if it's not, you know, you're in trouble. But so, you know, what, you know, mathematically it's been shown that bootstrap works in the long run, and because random sampling should work in the long run. And so anyway, what this plot is showing, if it's not clear, okay, so over here we've got the result of what happens to alpha based on our simulated data sets, okay? So on our simulated data set, when we know what the true population looks like, we see that, okay, most of the time, yeah, we should invest about 60% in X or something. You know, maybe one time in our simulated data set, like Y had a lot of variation, and so we said, okay, we should invest like 90% in X or something, right? But most of the time in our simulated data sets, we're getting something around the true answer, okay? This is the result of the bootstrap, okay? And in the bootstrap, okay, we are taking the one data set that we have and we resampled it, and we did this 1,000 times. And so we don't have the real population, we just have our fake bootstrapped population, which we've basically taken our sample and we've cloned it a bunch of times and resampled it. And here, our estimates end up being, if you look at the axis, you know, the center is a little bit lower. It's not at 0.6. They draw this purple line at 0.6 for whatever reason. But the center is really probably around like 0.55, 0.57. If you look at this histogram, it looks a little bit different, okay? Similar shape, similar spread, slightly different centers, okay? And so, so basically we get some agreement, but the bootstrap's not exactly the same. And here, the difference is more pronounced if we just make a box plot, and we can see that the median of the true thing is like right at the value of 0.6, and the median of the bootstrap thing is a little bit lower. But if you look at the spread, it's very similar, okay? And so bootstrap does give us, by using bootstrap, and if we were to use this to estimate the standard error, like we can get a pretty good estimate of what it should be, okay? But again, bootstrap is highly dependent upon your current sample of data, and that's the problem in all of life, is that we don't know if the sample we have is any good or not, okay? And so here's just an illustration of bootstrap. So if your original data had 3 observations, 1 bootstrap sample, you're basically, duplicating this 1 billion times, and then you draw with replacement, or you just sample from here with replacement. So you get observation 3, 1, and 3. You got the same observation more than once. Here you got 1 of each observation, and here you got observation 2 more than once, and something like that. And so that's basically what happens when you do bootstrap. I didn't think it was necessary to put this in the slides, and it gives us a good idea of kind of the variation, but you know, always a little bit of uncertainty there. All right, any questions? We're all good? Okay, all right. I have to pick out problems for you guys to do from chapters 4 and 5. How do you guys feel about these homeworks? I like the questions. I think they're good questions, but I don't know. You guys, they're all right? We're doing our best to answer the questions ourselves. I know the answers are out there on the internet, but we're doing our best to answer them ourselves. Okay. All right. We'll end a couple minutes early, but I know you guys have discussion immediately after. And I'm gonna take off because I'm going on a family get together tomorrow for Independence Day. It's going to the beach. You guys don't need to know this, but I have to wake up like super early, so I'm taking off. All right. Have a great 4th of July and great weekend. I hope you guys get to enjoy part of your summer, even though you're taking classes and whatnot. I'll post homework too up probably later tonight. All right, we'll see you guys.